In this lesson, we'll be studying the preparation of alkenes. There are essentially two common laboratory methods: the dehydrohalogenation of a secondary and tertiary alkyl halide, and dehydration of an alcohol. So in order to understand the alkene preparation reactions, we need to know something about alkene stability. Basically, alkenes become more stable with increasing substitution on the doubly bonded carbons. In this illustration, I have alkenes that are substituted in 5 different ways. On the far left, we see what's called a tetrasubstituted alkene, which means all 4 of its hydrogens have been replaced or substituted by alkyl groups. And these are more stable than a trisubstituted alkene, which has 3 of its hydrogens replaced or substituted by alkyl groups. And this in turn is more stable than a disubstituted alkene, which has 2 of its hydrogens replaced with alkyl groups. And this is more stable than a monosubstituted alkene, which has 1 hydrogen replaced by an alkyl group, which is more stable than an unsubstituted alkene, which has none of its hydrogens replaced by alkyl groups. Now, the reason for this stability trend is thought to be due to hyperconjugation of the pi electrons with alkyl sp3 orbitals. Now, the concept of hyperconjugation has already been discussed in another video entitled Alkenes Electrophilic Addition Reactions, so I won't take time to review it here. In the case of the disubstituted alkene, there are 2 possible stereochemistries. With the alkyl groups on the same side, that would be the cis or Z isomers. We could also have alkyl groups on the opposite side of the double bond, which would be the trans or E isomers. Comparing those 2 disubstituted isomers, turns out that the E isomer is slightly more stable than the Z isomer, simply because if the alkyl groups are on opposite sides, there's a bit more room and less crowding for that stereochemistry. So let's look at the preparation of alkenes. There are 2 methods in use. The first is called dehydrohalogenation. It means that we're removing a hydrogen and a halogen, and this works only with secondary and tertiary alkyl halides. So here's a hydrogen and a halogen on adjacent carbons. The halogen can be chlorine or bromine or iodine. So we're going to liberate or eliminate hydrogen chloride or hydrogen bromide or hydrogen iodide from adjacent carbons with a strong base, and a pair of electrons remains behind, giving us the alkene. Now the acid that's released from here, HX, is neutralized by the KOH, producing water and the potassium halide, either potassium chloride, potassium bromide, or potassium iodide. And that acid-base reaction is very favorable because we have a strong base reacting with a very strong acid. That's part of the driving force for this reaction. KOH is used because it is uniquely soluble in ethanol, and it's the solvent for the reaction. So here is the hydrogen and the halogen to be removed from adjacent carbons. So the acid HX, HCl, HBr, HI is removed and is neutralized by the base if it's hydrogen bromide with KOH. The products are water and KBr. In these reactions, there's no carbocation intermediate that forms, and therefore no carbocation rearrangements can occur, and that's a good thing. There are in fact 3 electron transfers that occur simultaneously in this concerted reaction mechanism. It's called concerted because they're done in concert, just like many instruments playing together is in concert. Likewise, 3 electron transfers occur simultaneously or in concert. You must remember that only secondary and tertiary alkyl halides work. Methyl and primary alkyl halides will undergo substitution rather than elimination with hydroxide ion. Well, it's time for a new rule. It's called Zaitsev's rule, sometimes Saitsev's rule. I believe it's a Russian name, and it seems to be some difficulty in translating it into English because both spellings appear in the literature. In any case, in Zaitsev's rule, it says that in elimination reactions, which by the way are E2 reactions, the more highly substituted alkene is the major product in a product mixture. This first alkene is 1-bromo, 2-methyl cyclopentane. And this is a secondary alkyl halide. It is an electrophile. It's secondary because the alpha carbon, the carbon that bears the functional group, is bonded to 2 alkyl groups. Next to the alpha carbon is what's called the beta carbon, second over, and there are actually 2 beta carbons in this compound, one on either side of the alpha carbon. In this reaction, hydroxide will remove a hydrogen ion from one of the beta hydrogens. In this case, let's look at the lower one first. Hydroxide is a strong base, removes hydrogen ion, leaving the pair of electrons behind, and this is the acid-base part of this reaction mechanism. Now, when the hydrogen ion is removed, those pair of electrons that remain drop down here to form the pi bond in the alkene product. But in order to accommodate another pair of electrons, this alpha carbon has to break a bond. And bromine is the leaving group, and it's a good leaving group. And so the new bond is accommodated. This type of reaction, an E2 reaction, is called a concerted reaction because all 3 of these electron movements occur at exactly the same time and there are no carbocation intermediates formed. This first set of reaction sequence will give us this first product, which is called 1-methyl cyclopentene. Now, there is a second beta carbon with a beta hydrogen on it, and when hydroxide collides with it, the same sequence occurs. The hydrogen ion is abstracted, the pair of electrons remain behind and form the pi bond in this position, provided that the leaving group leaves, and again, a bromine is a good leaving group. This second set of reaction sequence gives us a second product, which would be 1,2,3-methyl cyclopentene. So we do get mixed products in this elimination reaction because there are hydrogens on both beta carbons. Now the 1-methyl cyclopentene is trisubstituted. So this alkene carbon is disubstituted. On the other side, it is monosubstituted. So 2 plus 1 makes 3. It's a trisubstituted alkene. And we'll see that is the major product, or the Zaitsev product. When we compare it to 3-methyl cyclopentene, this alkene is only disubstituted. One substitution here and one over here. 1 plus 1 makes 2. It's disubstituted. It's less substituted than the trisubstituted, therefore it is the minor product because it's the less stable product. The second alkyl halide would be 1-chloroethyl. So this is a complex substituent with carbon 1 and carbon 2, and the chlorines on carbon 1, hence we have 1-chloroethyl in brackets cyclohexane. Well, it is also a secondary alkyl halide. The alpha carbon is bonded to 2 other carbons. That makes it a secondary alkyl halide. It is electrophilic. There are again 2 beta carbons, and therefore there are also 2 beta hydrogens, so we can have reactions occurring at both sides of the alpha carbon. Let's consider the one to the right first. The hydroxide ion, the strong base, abstracts a hydrogen ion in a neutralization reaction. That means the pair of electrons remains behind and forms the new pi bond here, provided that the leaving group makes room for it, and it does. Chlorine's a good leaving group. It forms a non-basic, stable leaving group, chloride. And that reaction sequence gives us this first product, which would be called vinyl cyclohexane, or could be called cyclohexylethene, probably more proper. But remember that we have a second beta hydrogen, and so when a hydroxide ion collides here, it removes that hydrogen ion. leaving the pair of electrons behind to form the pi bond here, and as long as the chloride leaves. And again, all three of these electron transfers occur simultaneously. No carbocation is formed. We say it's a concerted reaction. That second reaction sequence gives us this second alkene product, which is ethylidene. This is an ethylidene group. Ethyl doubly bonded to a single carbon is an ethylidene cyclohexane. Now, the ethylidene cyclohexane is trisubstituted. There are two substituents on the left-hand alkene carbon and one on the right. 2 plus 1 makes 3. It's trisubstituted. You'll see that that is the major product called the Zaitsev product. In this alkene on the left, vinyl cyclohexane, this alkene carbon is unsubstituted, and the one on the left is monosubstituted. Hence, it is the minor product because it's the less stable alkene, and the more stable alkene preferentially forms. This last alkyl halide is 2-iodoethyl cyclohexane. So here is carbon 1 in the alkyl substituent. There's carbon 2, hence it's 2-iodoethyl. It's a complex substituent. Now it turns out that this alkyl halide is only a primary alkyl halide because the alpha carbon is only bonded to one other carbon, and this will not undergo an elimination reaction. It does not produce an alkene. Instead, we get substitution. I'll explain why on the next slide, but let's finish this. When the hydroxide ion collides with the backside of the carbon, backside from where the leaving group is, the leaving group simply leaves, and the reaction takes place on a single alpha carbon. No elimination occurs. In this case, we're going to get a hydroxyl group replacing iodide. We get an alcohol. This alcohol is called 2-cyclohexylethanol. So to recap, what's happened here is when you use a methyl or primary alkyl halide, you don't get elimination. Instead, you get substitution, and that is called an SN2 reaction, substitution nucleophilic second order. That's the subject of a second course in organics. I won't say any more about that. However, when you use a secondary or tertiary alkyl halide, we get elimination. This particular kind of elimination is E2, which you'll study in the next course. Let me see if I can briefly explain the reason for the competition between substitution versus elimination using a strong basic nucleophile. So again, with methyl or primary alkyl halides we get substitution, whereas with secondary or tertiary alkyl halides we get elimination. Hydroxide is not only a good electron donor to a carbon, but it's also a strong base, and it can remove a hydrogen ion. So it has two competing abilities here. Here I've drawn methyl bromide, which is a methyl halide, ethyl bromide, which is a primary alkyl halide, the alpha carbon bonded to one other carbon, isopropyl bromide, in which the alpha carbon is bonded to two other alkyl groups, and here I have T-butyl bromide, in which the alpha carbon is bonded to three other alkyl groups, hence it's a tertiary alkyl halide. Now, when the hydroxide group collides with a molecule, the front side, if you will, this side here is blocked by the existing halogen, so no reaction is going to occur there. In order for substitution to occur, the hydroxide would have to strike the backside of the alpha carbon. And in the case of a methyl halide, it's quite unhindered. These are small hydrogens, and it's easy for the hydroxide to hit the backside of this carbon, causing a substitution reaction in which the halogen leaves in place of it. In the case of a primary alkyl halide with only one alkyl group attached to the alpha carbon, there's still lots of room, and the hydroxide preferentially quickly collides with the backside, displaces the halogen, giving us a substitution reaction. But that situation changes when you get to a secondary or tertiary alkyl halide. In the case of a secondary alkyl halide with two alkyl groups attached, the backside of the alpha carbon is mostly hindered. It's very difficult for a nucleophile to hit it. So since it's very slow at doing that, instead it exercises its other ability, which is to remove a hydrogen from one of the beta carbons, producing the alkene in an elimination reaction. In the case of a tertiary alkyl halide, this blockage is complete. There's just no way a nucleophile is going to hit the backside of that alpha carbon, and so the only option available to this reactive hydroxide is to remove one of the hydrogens from one of the alpha carbons, causing an elimination reaction. And so this scale shows us a decreasing rate of substitution reactions. Methyl alkyl halides react very quickly by substitution. Primary is quite quick as well. Secondary is slow, and very slow, and tertiary is basically not at all. In order to learn the second method of alkene preparation, that is the dehydration of alcohols, you will need an understanding of the relative stability of carbocations and the mechanisms of carbocation rearrangements, namely the hydride and methide shift. Now, this theory is presented on the next 4 slides, but these same 4 slides are also presented in the video Alkenes Electrophilic Addition Reactions. And so if you've already studied this content in that video, you may want to skip the next 4 slides, move directly to the details of the alkene preparation by dehydration that follows on slide 11. Not all carbocations are alike. Look at the relative stability of these carbocations. A tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation, and that is more stable than a methyl carbocation. So more alkyl groups attached to the carbocation makes a carbocation more stable. Fewer alkyl groups attached makes it less stable. So why is that? Take a look at this energy diagram for a chemical reaction. The energy of the reactants is shown on the left. The energy of the intermediates in the reaction is shown in the center. The energy of the products of the reaction is shown at the right. Notice that for reactions that involve carbocations, the tertiary carbocation intermediate has a much lower activation energy, this energy, than that of less substituted carbocations, like the primary carbocation has a very high activation energy or energy hill to overcome. And so a reaction will naturally follow the lower energy path and produce the low energy path product. Well, we've just stated that a tertiary carbocation is more stable than a primary, and for that matter more stable than a secondary carbocation. So the next logical question will be, well, why is that true? Well, there are 2 reasons given. It turns out that carbocations are stabilized by inductive effects and hyperconjugation with alkyl groups. Let's look first at the inductive effects. Alkyl groups, whether they methyl, ethyl, propyl, whatever they are, will donate electron density or shift electron density through their sigma bond, carbon-to-carbon sigma bond, toward the electron deficient carbocation, in much the same way that a more electronegative atom will draw electron density from the atoms it's bonded to. And if you think about Linus Pauling's electronegativity values, a neutral carbon is given a electronegativity value of 2.5, and a carbocation has to be more electronegative, whether it's 2.6 or 2.7. It definitely is more electronegative than a neutral carbon, and so it would in fact hog or draw some electron density from the alkyl groups through the carbon-to-carbon sigma bond, the inductive effect. The other rationale is hyperconjugation. So recall that a carbocation has an unhybridized, empty 2pz orbital, ready to accept electrons. Now, at least one of the 3 carbon to hydrogen sigma bonds in any alkyl group would be aligned and overlap slightly with this empty 2pz orbital, and therefore could donate some electron density, kind of like resonance, into this empty 2pz orbital. And the more alkyl groups you have attached to the carbocation, the more hyperconjugation can occur. So it's an observed fact that tertiary carbocations with 3 alkyl groups attached to the carbocation are more stable than a secondary carbocation with 2 alkyl groups attached to the carbocation. In turn, more stable than a primary carbocation with only 1 alkyl group attached, and in turn, more stable than a methyl carbocation with no alkyl groups attached, only 3 hydrogens. Carbocation rearrangements. Well, during reactions, carbocation intermediates may rearrange to form more stable carbocations. That is, a primary carbocation will spontaneously reform into a secondary carbocation, and that may spontaneously reform into a tertiary carbocation by one of 2 mechanisms, what's called a hydride shift or a methide shift. Now, hydride is the anion of hydrogen. Notice this has 2 electrons and a negative charge. It's actually hydride, not hydrogen. Similarly, methide is the anion of a methyl group. This carbon actually owns 5 electrons. It shares 3 electrons with the 3 hydrogens and owns a pair. It's a carbon anion, a carbanion. So let's look at the mechanism of a hydride shift. Here I have 3-methyl, 1-butene. Here's our nucleophile in the alkene pi bond, and here's the electrophilic part, the hydrogen in HCl. Now the hydrogen ion will add to the less substituted carbon, Markovnikov's rule, producing the more stable, more substituted carbocation. This is a secondary carbocation. And the leaving group, chloride, is a fair nucleophile, and upon collision with a very good electrophile, all carbocations are good electrophiles, it will instantly bond and produce this product, which would be 2-chloro, 3-methyl, butane. But only about 50% of the product is 2-chloro, 3-methyl butane. Some of it is 2-chloro, 2-methyl butane. How does that form? Well, it turns out that right next door to this secondary carbocation is a tertiary carbon with a hydrogen on it. And that hydrogen, with its pair of electrons, and that's what this arrow is showing, it's right from the bond, not from the hydrogen, but from the bond, we're saying that the hydrogen and its pair of electrons will shift over 1 carbon. Here it is attached, and that produces a more stable carbocation. This is a tertiary carbocation because it's bonded to 3 alkyl groups. It's a spontaneous and unstoppable reaction. And when chloride collides with that carbocation, we get this product, 2-chloro, 2-methyl butane. Now, as a general rule, mixed products will form when carbocation arrangements occur, and the major product is usually the one that's formed from the more stable, more substituted carbocation, and the minor product is usually the one formed from the less substituted carbocation. In this case, it's roughly 50-50. Well, that's a hydride shift. What about a methide shift? So here's an example of a methide shift. 3,3-dimethyl 1-butene. 1,2,3,3-dimethyl 1-butene reacting with HCl. Here again is our electron donor, our pi bond. Here's our electron acceptor. Following Markovnikov's rule, when this pi bond opens, the hydrogen that combines will add to this carbon, the less substituted carbon, so double bond CH2 becomes single bond CH3, producing the more stable, more substituted carbocation. And the leaving group, chloride, when it collides with this carbocation, will add, producing this product, 3-chloro, 2,2-dimethyl butane. But once again, that's not all the product. We have a mixed product. We also have some 2-chloro, 2,3-dimethyl butane. How does that form? Well, notice that right next door to the secondary carbon is a quaternary carbon, and with methyl groups, one or more methyl group, and as long as it has one, that methyl group can move over with its pair of electrons. That therefore is a carbanion, a methide group, and here it is moved over, producing a more stable, more substituted tertiary carbocation. When chloride collides with it, we're going to get addition at this spot, producing 2-chloro, 2-methyl-butane. Again, the major product is usually the one formed from the more stable, more substituted carbocation. So the second and final method of preparation of an alkene is by dehydration of an alcohol. That means the elimination of water using a strong acid catalyst such as sulfuric or phosphoric acid. This can be done in water or sometimes in an ether solvent, and if so, usually tetrahydrofuran. In this reaction, a hydrogen and a hydroxyl are eliminated or removed from adjacent carbons, producing the alkene pi bond and eliminating water. Heat, of course, is required to do this. The mechanism is elimination, but it's classed as an E1 mechanism, which does in fact involve carbocations, unlike the E2 elimination we looked at earlier. So let me take you through it. Here we have 1-methyl-cyclohexanol. Now the formation of the alkene involves the loss of a hydroxyl group, and it's just not going to happen as it is, because if it leaves the way it is, it forms hydroxide, and it's a strong base, and it's going to be very difficult to do. So by adding acid, we protonate the hydroxyl group to make a better leaving group. So the hydroxyl group is a poor leaving group because it forms the reactive hydroxide ion. Protonation with strong acid forms an OH2 plus, an oxonium ion, which is a better leaving group. It'll leave as an unreactive water molecule. So here is our nucleophile. In the first step, the oxygen, you can even think of it as an acid-base reaction in the first part. And here is our electrophile, and you can think of it as an acid. Remember that alcohols, like water, are weak bases with a pKb of approximately 16, and hydronium ion or sulfuric, they're strong acids. And so when they react, the hydroxyl on the alpha carbon collides with a hydrogen ion, and it becomes protonated, forming our protonated alcohol, which is a better leaving group than the hydroxide. And on heating, we drive out water. This is the rate determining step because it's going to form a carbocation. Here's the water of elimination. The second step involves removal of a hydrogen ion from one of the beta carbons. And here's our nucleophile for that second step. Water removes a hydrogen ion from a beta carbon. And as that happens, the pair of electrons remains behind and comes back here to form the pi bond to satisfy the carbocation intermediate's requirement for electrons, giving us 1-methyl-cyclohexene, and the water plus hydrogen ion regenerates the catalyst in the last step. The order of reactivity, or the ease of reactivity, in this alkene formation reaction is that tertiary alcohols react most easily, most readily, most quickly, using only a relatively low concentration of sulfuric acid at a relatively low temperature, 85 degrees C. Secondary alkyl halides would be more difficult to work with, and primaries would be most difficult of all to convert into alkenes. And for that, you would need concentrated sulfuric acid at relatively high temperatures. And the difference between tertiary, secondary, and primary alcohols has to do with the stability of the carbocation intermediate. Tertiary carbocations are more stable and therefore more readily formed than secondary or primary. When a carbocation occurs, remember that carbocation rearrangements can occur. Primary carbocations rearrange to secondary, secondaries to tertiaries, whenever methide or hydride shifts can occur. So let's look at the mechanism of dehydration of an alcohol again, this time with a carbocation rearrangement. So we need to remove a hydroxyl group from one carbon and a hydrogen from an adjacent carbon. Well, there is none, but we'll deal with that in a bit. First of all, in order to remove this hydroxyl group, we need to protonate it. So the addition of a strong acid will protonate that, producing this oxonium ion, which is now a fairly decent leaving group. Upon heating, it drives out water and forms this primary carbocation. In order to get an alkene, we have to remove a hydrogen from a beta carbon, and the beta carbon has no hydrogens. However, it is a quaternary carbon with alkyl groups on it. It has a methyl group which can move over by means of a methide shift, producing a tertiary carbocation. And this carbocation is not only more stable than the primary, so it's going to form, but secondly, it has beta hydrogens on both sides of it. So when another nucleophile, in this case water, collides with this beta hydrogen, it will abstract the hydrogen ion, forming hydronium ion, and the pair of electrons remains here to form the alkene carbon and bond, and here it is here. This is 2-methyl-1-butene. Now let's consider the other beta hydrogen over here. When water collides with this hydrogen, it's going to be abstracted. The pair of electrons remains behind to satisfy the electron deficiency of this carbocation and produce a pi bond right here. This will be 2-methyl-2-butene. Now 2-methyl-2-butene is a trisubstituted alkene. This alkene carbon is disubstituted, and this is monosubstituted. 2 plus 1 makes 3, and that is more substituted and therefore more stable and is the major product as compared to 2-methyl-1-butene, in which we have a no substitutions on the left, disubstitute on the right. This is a disubstituted alkene. It is the minor product. And again, the hydronium ion catalyst is regenerated. So this is our last example in this unit. One more practice problem, dehydration of an alcohol. Now in this case we're using isopropyl alcohol. We want to dehydrate it to an alkene. We're going to have to add a strong acid and heat. The acid will protonate the hydroxyl group, forming an oxonium ion, which upon heating will eliminate water molecule and give us a carbocation in this secondary position. It's the most stable carbocation that can form, so there'll be no rearrangement. In the next step, water molecule will have to remove a hydrogen from one of the beta carbons. The beta carbons are the same on both sides. When the hydrogen ion is abstracted by the water, the pair of electrons remains behind and forms the new pi bond to form the alkene, in this case propene. And there's our hydronium ion acid catalyst regenerated. One last example here. This is cyclopentyl methanol. We want to form an alkene from it. We're going to add strong acid and heat. Again, the alcohol is not a good leaving group, but when we protonate it with the acid, it forms an oxonium ion, which upon heating will lose water, giving us this carbocation. Is there a hydrogen on the beta carbon? Sure, right there. And so water molecule can remove the beta hydrogen. The pair of electron remains behind to satisfy this carbocation, and we'll get this product, which is methylidene cyclopentane, and the hydronium ion acid catalyst regenerated. But notice that this is only a primary carbocation, which is the least stable, and right next door to it is a tertiary carbon with a hydrogen that can move over. So the very same hydrogen that in one molecule would be abstracted to form this alkene in another molecule can hop over here by a hydride shift and give us a more stable carbocation, in this case a tertiary carbocation. Now this carbocation does have beta hydrogens on both sides of it, so either hydrogen from either one can be removed. Let's consider this one here because it'll give us a different product. Our beta hydrogen is removed when it collides with the water molecule. The pair of electrons remains behind, and that satisfies our carbocation, giving us this alkene and hydronium ion. This is 1-methyl-cyclopentene. Now if you look at the degree of substitution of both alkenes, this lower alkene is trisubstituted. There are 2 replacements of hydrogen on this carbon and 1 here. 2 plus 1 is 3. It's trisubstituted. And in methylidene cyclopentane, no substitutions of hydrogen here and 2 here, so it's disubstituted. So 1-methyl-cyclopentene is more substituted, it's more stable, it is the major product, it's the Zaitsev product, whereas methylidine cyclopentane is the minor product. So dehydrohalogenation and dehydration are the most common laboratory methods of preparations of alkenes. And the principles in this lesson are used again later in the course and in subsequent organic courses, so find the time to review this lesson as often as needed until the material becomes familiar to you. Now there are several other related videos that you should watch. Intro to Organic Nucleophiles and Electrophiles, Polarizability, and the Efficiency of Leaving Group, Alkene electrophilic addition reactions, and alkenes oxidation and reduction reactions. Stick with it, you'll get it.